Okay, so welcome back, and we will continue to discuss about model selection, chapter 4, model selection. So I said the one purpose of this chapter is to convert many theoretical results that we proved, which are about, how to find some strong guarantee from an sample-based estimation into an algorithm, at least in a very, at least some form of the algorithm, which may not be implementable, but still carry some idea of the algorithm, Okay, so, right. So one thing that we talked about so far is that we start with something very basic. So a quick review. Something very basic, which was empirical risk minimization. The idea is quite simple. Given a set of samples, we want to find hypotheses that minimize empirical risk. In a sense, that minimize an error from a sample that we have. So that is the idea of empirical risk minimization. And that's the kind of idea that comes up to you whenever you see this type of a learning problem. But it turns out we can do a lot better by putting some structure on a hypothesis set. So instead of having one monolithic hypothesis set H, we say our hypothesis set is structured. So it's a union of some smaller hypothesis set, such that this smaller hypothesis set is increasing with respect to the index. So if we have we consider such a scenario and design an algorithms that exploit this structure, essentially the idea of the algorithm is to search for an appropriate hypothesis set, HK. So the big idea is to search for a good hypothesis set HK and a good hypothesis in HK. And the algorithm that we looked at were structural risk minimization that does this two-level search at the same time. So it searches for a good hypothesis and a good hypothesis set and a good hypothesis at the same time. So it do this two-level search at the same time using the objective, which is coming from the generalization bound. So, and that objective is written as a fk of h, that is written as, that has a usual empirical risk component, but it has another component that measures the complexity of the smallest hypothesis set that contains a hypothesis H. So the measurement was the Rademacher complexity of a hypothesis set that contains H, smallest hypothesis set that contains H, and then some penalty that's related to the index. So K of H by 5. So the first part, in a sense, try to minimize the errors with respect to the sample. And then the second part, try to find the simplest hypothesis set, simplest but good enough hypothesis. So I give a balance between the complexity of a hypothesis. If we hypothesis set is complex, this part will become small. And then on the other hand, hypothesis set is complex. The other part will become large. So you put the right balance between the put the right balance between the complexity of the hypothesis set, the penalty that we pay for it, and the benefit that we gain from the complexity. And the other algorithm, but I said this SRM is more like a theoretical algorithm. That's because this Rademacher complexity is not we cannot really compute it. So something that becomes a bit closer to the real algorithm is cross-validation. And that is, so I explained the idea or the algorithm of the cross-validation, but didn't give you analysis about the cross-validation. So the cross-validation works like this. So it has two components, okay? So I mean, most of the algorithm has two components. One component corresponds to, this empirical risk part. So you want to do something with the empirical risk. You want, with respect to some set of samples, we want to minimize each error. Okay, and it has another component that is designed to deal with this generalization. So we want to be sure that what we can, the conclusion we can obtain by minimizing the empirical risk is a good estimate, good predictor for what's gonna really happen in the real risk. So empirical error is a good indicator for the real generalization error. And we want to have such a guarantee. So we want to have, some component that's related to managing the complexity, which is given the second part. So the cross-validation achieve, in a sense, they touch these two parts in the following way. It's a given set of samples, the given sample of examples, x1, 1, 2, xm, ym. What it does first is that it splits S into two parts, so S1 and S2. And the first part, S1, its size is, it contains 1 minus alpha m examples. The second part contains alpha m examples. So it split as our sample into the two samples, S1 and S2. And S1 is sometimes called a training set. S2 is called validation set. And then it does the following. So what I'm describing to you is not really the highly optimized algorithm. It's more like an idea that will lead to the implementable algorithm, okay? So what we do in the second step is that for each k, we find H Theorem S1 k. So we use only samples in S1 and consider on a hypothesis of HK, and we find some hypothesis that minimize the empirical risk. That's going to be argmin of H in HK, such that it minimizes empirical risk with respect to S1. H. And then once we do it, the last step is now we find the return. Okay. So important bit is that we are using S1 here to find a good hypothesis in each hypothesis class. But then instead of picking the winner based on among these hypotheses from each hypothesis class, using S1, we use S2 to find the winner. So the winner, which we're going to return, cross-validation with respect to sample S is going to be argument among H S1K Theorem and such that it minimizes empirical risk with respect to the validation set. So note that we are now using S2 to evaluate this. So the first, this is step number 2 is related to what I mentioned here. Okay. This one is related to if you match what's going on here with what happened with SRM. This step 2 is a bit related to the minimizing the empirical risk in the SRM. And step 2 is a bit related to, this measure. It's more than the measure of this Rademacher complexity plus some extra, the square root term in SRM, but it's closely related to this. It tried to measure the real generalization. Okay. So then the final output is going to be this H, the CVS, that's going to be the result of this algorithm. Step 4, let's return HSCV. Okay, what's good about this? Compared to the structural risk minimization, it's much simpler. We don't have to compute, especially we avoided the computation of Rademacher complexity. So cross-validation, although as I stated, is not really a highly optimized algorithm, or maybe not very implementable. It's getting a bit closer to the realistic algorithm that we may use in practice. Okay. And okay. So then the next natural, but on the other hand, it's not perfect. Okay. So we are gonna, in this algorithm, so we will, given a sample S, we have to use split sample into S1 and S2. And then only S1 is used to find the solution that minimize the risk in each hypothesis set. And only S2 is going to be used to find, to evaluate how good hypothesis from each hypothesis set, the quality of the generalizability of a hypothesis from each hypothesis set. So S2 is used here only, S1 is used here. Now, if we split such a way that S2 is large, so then the information we can get in step 3 is going to be very accurate. The evaluation that we're gonna use using S2 is gonna be very accurate. But so we will pick the right winner in some sense. But the candidates for this winning process, which is obtained in step 2, may not be very ideal because S1 will be small. So using small S1, we may be unable to find a good hypothesis in each hypothesis set. Okay, so large S2, step 3 will become very good, but step 2 may be not very ideal. On the other hand, if we use a small S2, now the problem is what we're gonna get in step 2 is gonna be very good because the S1 will be very good in that case. On the other hand, what we're gonna get in step 3 may not be so ideal because the size of the sample that we use to evaluate each candidate from each hypothesis set is gonna be small, so that our evaluation may be not so accurate. So what should we do about this? So what I'm gonna tell you next, which is the n-fold cross-validation, is designed to overcome this problem. But before talking about this, what I will do now is I will show you some analysis about the cross-validation, and then move on to n-fold cross-validation. So the plan today Yes, we first talk about some the analysis of cross-validation. Then I will tell you about the idea of n-folds cross-validation. Then if time permits, we're going to talk a little bit about regularization and also the convex surrogate loss. So these two also address some of the issues that, these two are the idea that will allow us to move these idealized algorithm into something more realistic. Also, these two address some issues that that appears in the structure risk minimization. In all these algorithms that we are talking about, like a structure risk minimization, cross-validation, and n-folds cross-validation. So let's start with the analysis of cross-validation. So the analysis in the textbook, I'm not entirely sure whether it's correct. The textbook of cross-validation. So what this analysis tried to achieve? So this analysis tried to achieve that, okay, if we do cross-validation, what kind of things we can guarantee? So that's what we want to get out of this theoretical analysis. Then before giving you the real results, so the textbook tried to show some theorem that compares the performance of cross-validation and the structure risk minimization. I'm not entirely sure that the result in the textbook is correct. So instead, I will give you my own modified version of the theorem, which I think say something more accurate. Okay. So here's some form of the theorem. Four. So this one, say, for all problem and for size of the sample for delta and the probability that risk, so probability is over samples, m, probability of the risk of what we get from cross-validation is bounded above by the best among the empirical risk minimization. H1K Theorem. And no. So with high probability, the risk of what's returned by the cross-validation will be bounded by something that I'm writing on the right-hand side. Yes. Okay. Minus delta. And then if you combine this result with what we proved about ERM, then you can refine the result a bit, into something better. Okay. Now, what's important about this? One important bit is that the guarantee that we can obtain here is with respect to, I mean, so in the bounds, we have when the so previously our bounds get tighter based as the number of samples increase, but then the number of samples that really help to improve the bounds is alpha m, which is the size. So this is the size of validation set. So what it tells us is that the validation set, I mean, is the one that allows us to say, I mean, allows us to give a guarantee. Okay. On the other hand, the role of S1 is there to say, if S1 is large, then I mean this risk is going to be, I mean, with high probability, this risk is going to be small. So the S1, the size of the S1 play a role to minimize the first component, I mean, this first part of this bound. And now if you combine, so if the above is combined with the bound for SR, ERM, you can get some complete story. No, don't worry about this. Okay. Yeah, don't worry about this. Ignore what I tried to say. Okay, the question is, now the question becomes how we can prove this theorem. And then the key part of the proving this theorem is the proposition 4.3 that gives us a uniform bound on the ERM solution. Okay. Some colors. So, yeah. And then we have different proposition. That the proposition say the following, exactly the same setting that I explained to you. And try all of them. For E and so for alpha. So actually for alpha has to be here. And epsilon. Then we have the following bound probability that Screamer K where this. So what this proposition tells us is that how good the sample the empirical risk is going to be with respect to the real risk for every the ERM solution. This one, okay. Let's see. Okay. So let's phrase it differently. I mean, phrase it different this way. Okay. Found it. Okay, so that's the proposition. So what does this proposition tell us? Proposition tells us that for for every empirical the solution of empirical risk minimization and each hypothesis, this guy, if we compare its risk and its empirical risk with respect to S2, and they they are very close with risk modular. I mean, these extra penalty terms that we are putting there. Okay. So it's the usual, the uniform bound that we have seen so far. So I mean, the reason I rush a little bit is because I want to use. So I thought if I just keep showing you the proof, it doesn't mean very much. So I want to, here's an exercise for you. Use this proposition to prove theorem 4.4. Okay, so I will give you 4 minutes so that you can use this proposition and try to prove theorem 4.4. And this bound is, I think, sorry about this, but let me just rewrite this so to the form that is a bit more familiar to you. So for all k, so that's the form. So probability for k, the difference between the real risk and empirical risk is bounded by the quantity in this proposition the probability is very high. So 1 minus delta. And then use this proposition and prove theorem 4.4. So I give you time until 9:35. So give three more minutes to solve this exercise. Okay, so let me show you how we can solve this exercise. So proof of 4.4. So the proof is quite simple. So what we do is that let's call this entire statement. Let's call this whole statement here inside the probability as call this statement as statement. Let's call it V2. And then the whole statement inside the probability. Let's call this as a V1. So this is V2 and V1. So if you do so, then all you need to prove is suffices to show V2 implies V1. Yeah. So if V2 implies V1, then the probability of V1 happens should be at least probability of V2 happens, which is already pretty high, so we are done. Okay, that's what we have to show. But we can rewrite V1 as follows. So we can, but V1 is equivalent to following statement, which say for K, the risk of HSCB is bounded above by risk of HS1 K Theorem plus square root of log K alpha and so on. So the other two terms that you see, in the statement. So we just move the infimums to the outside as a universal quantification. So these two statements are V1 is equivalent to this. So what we have to prove, that means that we just need to show V2 implies the new statement that we just obtained here. So the new statement that we just obtained here. To show this, showing this is not actually very difficult. We pick K, and then we have to show this inequality, and then we just do the calculation. R of HSCB, that is by V1, so smaller than or equal to S2, because HSCB is one of the solutions of empirical risk minimization with respect to some hypothesis set. So the V2 applies to HSCB, solution of cross-validation, plus okay, alpha n. Hypothesis set, index of hypothesis set containing the solution of cross-validation. Yes. So for delta 2 alpha. But because the way we obtain the cross-validation is solving an optimization problem. So if we replace this part, the solution of cross-validation by any other ERM solution from a different hypothesis, hypothesis set, then this part will become larger. So this is smaller than or equal to RS2 H ERM S1K plus in the same extra term. Two terms that's coming from this guy and this guy. So that these two guys are over there. So then now we are using the V2 again. Now this time, because it's V2 has an absolute value, we are using a different sign of the absolute value. So put a minus, so you can put minus here and plus here, and get an upper bound on the empirical risk. So if you do so, then here's what we get. And this is bounded above by S1, K, ERM, plus log K, alpha n, plus log 4 delta alpha n. And then there's something very similar is coming from here. So this guy comes from here, which is a log K HSCB. And the extra term is now can be observed here. So same as we have a 2 times here. And that's exactly what's stated in the theorem. So that completes the proof. So one thing you can notice is when we prove the generalization bound, our generalization bound is mostly about how the real risk or generalization error is bounded by empirical risk or empirical error, bounded above by empirical risk or empirical error. But to talk about performance of the algorithm, we have to go from so just like see here, we have to go from the real risk, the risk of what's computed by the algorithm, to the empirical risk of that guy, and the empirical risk of some other things that we are comparing, and then the risk again. So we need to give not just the upper bound of the risk, but also have a lower bound. So that's what's stated by the absolute value of this proposition, and that's what's being exploited here. And the proposition, proving the proposition itself is not very difficult. I just refer you to look at a textbook or for the notes that I posted in the course webpage. And the idea is just using Hopkins inequality, but this time we have to use both two sides, Hopkins inequality to upper as well as a lower bound. And then the other thing that we have to use is a union bound to deal with the universal quantification over K. Okay. So if you do so, then you can prove the proposition 4.3. That's the analysis of the cross-validation. And now let's move to the algorithmic discussion of an algorithm. The n-folds cross-validation. So the idea of n-fold cross-validation is a bit similar to cross-validation. At least the one that's described in the textbook is a bit similar to the cross-validation, but there is a key difference in in the philosophy. So in the case of cross-validation, we search for a good HK and a good H in HK. Not exactly the same time, but almost simultaneously. So maybe get a bit confused. SRM, this is a bit clear. Cross-validation is not entirely clear that this is what's happening. But if you compare this with what's really happening in n-fold cross-validation, then you will see what I mean by this almost simultaneously. Okay. Now, if you come the n-fold cross-validation, it's a really two-level search. It's a hierarchical search. So we first find a good HK first, and then find good hypothesis H in HK. So in both times, so we are given sample S, and we are using sample, all of the sample, every examples in the sample in the first step 1. Also, we use every examples in the sample in step 2. Okay. So what we do in 1 is that we try to find a hypothesis that generalize well with respect to the specific distributions for this specific learning problem. Okay. By generalization, we mean that if we find, for given a sample, if we optimize, we sort of give us ERM solution with respect to the sample. We want this ERM solution to be a good hypothesis in general, not just for the sample. And we want to find a hypothesis set that guarantees such a things. So we want to find a good hypothesis set in terms of generalization. That's step one. Step two is that once we find a good hypothesis set, we want to find a good hypothesis inside that hypothesis set. Okay, so that's the idea. We do this type of hierarchical search. Because it's a hierarchical search, both steps use all the examples in the sample S. Okay. See cross-validation, we split sample S into test set and validation sets. Nothing like this happens in enforced cross-validation. So now how does the algorithm works? So algorithm description. So once the first step is given sample, so it consists of x1, y1, to xm, ym. We split S into S1, S2, and Sn. So these are called folds. Each of them is called fold. It's called n folds. We split into the n folds. And then for each hypothesis set, we compute the following quantity. Computes cross-validation for this following quantity. That's 1 over n. So we repeat as many times as this number of folds. But what we do is the following. We say it computes we compute the empirical risk for the solution, ERM solution, obtained with examples without the without examples in SI. Okay. So this notation means all the examples except SI part is empty. This I part is empty. So we just remove examples in the ith fold, and then we put all the other examples together, and then use that examples to train and try to come up with a hypothesis that best explains the examples in all these examples except in the ith fold, using hypothesis at HK, and then come up with an ERM solution about this and evaluate with respect to something excluded, which is examples in ith fold, namely examples in SI. Okay. And we repeat this process for ni is equal to 1 to n. So in the first step, this is excluded, and the others are used for training in some sense. And then we evaluate with respect to S1. Second step, S2 is excluded, and all the others are included for training. And then as the examples in S2 are used to evaluate what we get by the training and so on. So we do this. And then step 3. All right, so let's call it step 3. We fix K star. That's something that have a minimum is cross-validation error. And then finally, once K star is chosen, then we find the hypothesis. In a hypothesis set HK star. And then that's what we return is something that minimizes empirical risk for every all the examples in S. So all the examples in S. So you can see that when so this is step 2 and 3, they are related to this first step that I mentioned above. So it uses all the examples in the sample in a way, in certain way, so that we can get information about each hypothesis set, whether the hypothesis set is good in terms of generalization or not. So that's the kind of measurement that we are doing. Then after the measurement, we figured out which hypothesis set is good. So that's chosen as a K star. And then in the next step, so we fix this hypothesis at HK, then try to find the hypothesis that gives the best performance when we use all the examples in S we use all the examples to find a good hypothesis in the hypothesis. So that corresponds to step number 2. So this idea of enforced cross-validation has more flavor of the hierarchical search. We search for a good hypothesis set first in terms of generalization. And then once we find a good hypothesis set, we fix that hypothesis set, and then we just try to find the best hypothesis in the hypothesis set. In both process, we use all the examples in the given sample. Okay. And this idea, and let me mention further things about this idea. The first things that I want to mention is this algorithm can be used not just as ERM, but with some other algorithm. Okay, what's really going on here? So what's going on is that this RCB, this is really try to evaluate. If you view it, is try to evaluate generalization ability of each hypothesis set when the algorithm that we are thinking about, a learning algorithm we are thinking about, is empirical risk minimization. And then this very idea can be used for the different algorithm. It doesn't have to be empirical risk minimization. If you use a different algorithm, use purple. If you use a different algorithm, sorry. So instead of ERM, we may use some different algorithm that's computed by, maybe some support vector machines or some other algorithms. So some other algorithms that may be given using sample S, including I, and hypothesis at HK, and that algorithm might return some other things. And then, but still the same idea applies. It's really try to test the generalizability of an algorithm when we fix its hypothesis set to HK. So this very idea applies. So they step 2 and 3 compute the generalizability of an algorithm with respect to a hypothesis set, and then we pick the winner, and based in the winner we apply the algorithm. So this, if we use this algorithm A, then this next step will use the same algorithm with respect to the HK star. So that's one thing. The second, when we can be a bit, I use the word generalization, and then I said the step 2 and 3 tests the generalization of an hypothesis set. We can make that word a bit more formal. So suppose the size of each fold are the same as 2. They're all, say, and let's call it M1. So the number of all the sample is M. Sample is M. The size of each fold is M1. So if that's the case, then what this step 2 and 3 compute is unbiased estimate. So these are C V of HK is an unbiased estimate of the following, which is expectation of S sampled from the, so we sample not M, but M-1 samples. And then run ERN algorithm over the sample S, K, hypothesis set K, then compute each risk. So this is a bit closer to what I told you, which is that so this is what's returned by the algorithm. R here is the real quality of the outcome of the algorithm, and the outer expectation say what's going to be what happens on average. So on average, what's going to be the quality of the output returned by the algorithm when algorithm is given M-1 samples. Okay, so that's what this data quantity expressed by expectation say, and this the R hat of CV of HK is a sample-based estimate of the quantity that I wrote on the right-hand side. And the quantity that I wrote on the right-hand side can be understood as a measure of on the generalizability of HK. So, and then this, R hat of CP can be understood as a, in a sense, good estimate of this. So unbiased estimate means if you take an expectation, that becomes the same. Let me just make this clear. So unbiased estimate means that we take an expectation over sample S, then R hat CP. Okay. That is exactly the quantity that I wrote on the right-hand side. So that gives us some justification about what's really happening. What really happened in the N-fold cross-validation is to measure the generalizability of each hypothesis set. And based on these measurements, we pick the best hypothesis set and use that hypothesis set to find a good hypothesis inside that hypothesis set. Okay. So this, in some sense, closes the kind of high-level the key components of the model selection. But there are two other things that's discussed in the textbook, and these two other things are regularization and convex surrogate loss. So what is, why we are thinking about this? So then these two things actually come from some issues. So if you try to convert the idealized algorithm that we discussed so far into the real implementable algorithm, you will encounter a few challenges. The first challenge is that well, first kind of not challenge, but something that annoys you is there are two. The first issue is that, this specific organization of a hypothesis is very limited. So the countable family HK is too restrictive. So a countable family with especially SRM, HK increasing. I mean, for other algorithms, similar assumption is made. That's too limiting. I mean, why that is the case. So sometimes we want to have, I mean, uncountable family, for instance. We want to have a family like H of parameterized by gamma. Gamma is in the any real number, or maybe gamma is a positive real number. And you might think that, okay, I mean, looks like our family becomes large. So this is good in the sense that we can express many hypotheses because this family, we have all sorts of hypothesis set. So this will, will increase the things, but you may get worried that by having so many the family members like HR, there are uncountably many, and this may start to cause a problem. It turns out if you parameterize by instead of natural number, parameterize by the real number, and make this parameterization in some sense smooth or what I'm saying smooth or continuous is very informal words. It's smooth or continuous in some right way, then the optimization problem becomes easier. Okay, because we can exploit that extra structures that relates this parameter gamma and the hypothesis set. The hypothesis H and its index K, there are not many nice relationship between the two, but in the case, even when there's a relationship, it's not very easy to exploit it in the design of an algorithm. But in this, if you have an uncountable family where the family is well parameterized by the real number R, then we can exploit this to design a better algorithm. So that's one limiting factor. Our family is too restrictive in some sense so that we cannot express many, so in terms of expressiveness, but at the same time, there's a specific parameterization by integers or natural numbers, causes an issue with an optimization. The second is that our risk, so you think about this empirical risk, it's defined like this. This is a very discrete function. So if you, it's really doing for each of the yi, so it's for y1 and y2, it's very discrete function. Okay. My words very discrete doesn't mean very much to you, but it turns out optimizing this directly it's not very easy. So if R head of SH, which appears in for instance, empirical risk minimization, or if this is a component of, if you use SRM, it's a component of optimization objective of SRM. The cross-validation, n-fold cross-validation, they're all the same. We need to solve, deal with some form of optimization problem involving this empirical risk. And this turned out to be very difficult computationally. So, one can show that in appropriate setting, so we have to refine the setting a bit more, but it turns out this is an NP-hard problem. So, but meanwhile, this empirical risk appears everywhere that we discussed so far, but it's a hard to optimize quantity. So what should we do about this? Okay, so the issues are that our countable family is too restrictive and maybe not very efficient. The empirical risk is hard to optimize. And then the regularization and convex surrogate loss are there to address these two issues. So, and then the idea of regularization is in some sense quite simple. So it's from the, if you view regularization in terms of model selection perspective, we have a family of a hypothesis set, typically parameterized by, by some positive real numbers. And then each hypothesis set and each index gamma, they are closely related. And the idea of regularization is to find something like, if you remember SRM, we have some extra terms like square root of log k and plus Rademacher complexity and so on. And just like in SRM, we want to have some quantity that's related to this gamma. Okay, so the regularization is to change optimization objective such a way that we do the model search, which is picking the right gamma, and then appropriate hypothesis in that model or in hypothesis set at the same time. And then I think the best way to understand the regularization is to see an example. So in one example is hypothesis set H gamma. It's defined by a function that take x and map it to sine of some w. So r. So choose k and so there are a few things that I need to explain. So the phi here is a map that take input x and map it to some vector in the k-dimensional space. So each of the hypotheses have this, that's one more, the sine function of some value a, you return +1 if a is non-negative. Otherwise, if a is negative, you return -1. So that's a sine function. So then each hypothesis has this form. You first map x to embed x to the k-dimensional Euclidean space by using phi. Then take an inner product with w. So it's a really linear function. And then after taking the inner product, you take the sign. And if the sign is non-negative, you return +1. Otherwise, you return -1. Now, this is a very general functions, which is it's a linear functions. And now for each hypothesis set is obtained by putting some constraints on the norms of this w. So this p, roughly speaking, you measure the size of w, vector w. It's defined by equal to 1 to k wi. So absolute value is p to the power of p, then take 1 over p. So typical norm is 2 norm. That's where p is equal to 2, but you can use a different norms. Okay. So p that from this discussion. So this p and k and phi, they are fixed. So for all the hypotheses, they use the same k, same p, and same this function p. But for hypothesis, depending on the hypothesis, gamma is different. Okay. Some hypothesis set, gamma becomes large. Some hypothesis set, the gamma is small. So you can see if you increase the gamma, the number of functions that's inside the hypothesis set becomes larger because of this inequality. Okay. Now, after doing this, the idea of regularization. So to talk about regularization, we have to impose some structure on the hypothesis set. So we have to parameterize hypothesis set with some positive, something like the real numbers, and we have to impose some structure so that there's a parameter of each hypothesis, like a W here, and then we can put some constraints on that parameter, and in terms of the norm and bound. And after doing so, then the learning problem process becomes like this. So the regularization solution over sample S is obtained. So finding our mean, where we are minimizing empirical risk of H, but at the same time, we also minimize P naught. Okay. So this W is the part of, it's a parameter that defines H. Okay. So what does this tell us? H is so what does this tell us is that this idea of some algorithm worked on regularization. This second component can be understood as the searching for a model. So it searched for a model, and at the same time, it also tried to minimize the errors errors of a hypothesis. So it tried to find a good hypothesis, tried to find a good model, smallest model at the same time. So that's the idea of regularization. And this becomes, by putting a structure like this, and then then this optimization becomes a lot more tractable optimization problem. And sometimes, not for this empirical risk, but for some other risk, similar kind of the optimization problem can also be expressed more directly in terms of some forms like something in the style of structural risk minimization, more explicitly about the searching for a hypothesis set and the hypothesis at the same. You can rephrase it in that way using some dualities in optimization. Okay, so that's it for today, and next time we will talk about the convex surrogate loss and then solve some exercises in the chapter 4. Okay, so I will stay here about 5 more minutes. So if you have any question, you can ask me. Okay, so thank you very much. Okay, you can ask questions about homework.